and serviced many renowned universities like the University of Wisconsin, National Taiwan University, etc. During his second postdoc at University of Electrocommunication Tokyo, Japan, he had worked on synthesis and non-destructive detection and characterization of germanium nanorods. Beyond his academic achievements, Dr. Sen is known for his strong work ethic, integrity, dedication to the society. It is my great honor to welcome you, sir.
Yes, I put.
Hello. Thank you for this introduction. I'd like to start my presentation, but before that, I just want to tell you this presentation that I'm going to tell you is more like a class and not like a lecture. Okay, so this is one of the new things that I could come upon with the help of some of the brilliant VIT Bhopal students. So a great thank to those seniors who were working in the lab. I should start the presentation like that. Okay. So please, I promise to please for Nami, Hemant, Suli, Ruchi, etc. Now, today I am going to tell you on how in literature you will find in many papers coming out with many different oxide materials and particles for antibacterial or other types of utilities. But it is very hard to find how the material is modified. And it can lead to different functionalities. It can lead to different kinds of effectiveness in different uses. Now, when I first came to this field, because mostly because of the electricity, I found that there are huge number of community reports. And the community reports was the first point where I started thinking that there is something to do. There is something which is related in her. So I was a physics person, so I think about the cause, not about the effect. And this is what was missing in the biology report. So I immediately started digging into the structure of the materials and whether there is distribution to the properties. So today's lecture will be structure related bio and physical properties of oxygen. See, my expertise is on semiconductors, semiconductors and magnetism and other things that I can see. But that is not what I'm going to talk about. I'm going to talk about something which is more relevant to you. So, at present, I have a group here where there are 3 different students in the science. I'm not coming to this one first. This one is more important because it contains some of the students who are even identified. This is one of the seniors, this is one of the seniors, this is one of the seniors. So these are the interior part here, they are interior part of the smart group. Okay. So these are some instruments that are represented in my lab. And I have detailed if you may want to know later on. But let's go to the subject first. Now, here I want to say how we do the research. Okay. So, in biology, what we do, we take a material and try to see what is the effectiveness of the material on a certain species. Okay, maybe an ancestor, it may be a bacteria, it may be some fungi, or something like that. Okay. But we do not look at the stuff, the material part, what it is. So this is what we do in our group. We make this samples with very good specifications and see there are several ways of synthesizing the material. Solvent is spinning atoms, and then the material is now we can maintain fields for biological purposes and also for material purposes. Then we have a very long history of different structural characterizations. Structural characterizations needed to understand how the properties will change. Let me give you what are the properties change. Suppose you have two atoms, okay? Now, if the two atoms are far away from each other, right? When you bring these atoms closer together, the electronic shells will start interacting with each other, right? And this will lead to the formation of a bond. Okay. Now this bond, if you keep these ions or atoms at a particular distance, they may have certain energy in them. If you change them by molecular orbital theory, you will be able to understand that the new energy states that it created will differ. So, as a result, what happens when you pull in a metal, if you pull the atoms farther, it will lead to different energy states that will be available to the metal. Now, so but how is it going to change the functionality of this material? So, you may have that if you address the synthesis condition such that there is a elevation in some form, maybe the crystallite that will grow to a different surface. Okay, it will prefer a different surface to be targeted. As a result, the surface animation changes and the surface charge changes. So when the surface charge changes, the interaction of this particle, the newly formed particle, with a biological particle, like cancer cells are negatively charged. Okay. Bacteria can positively charge or negatively charge. Now you can choose your material such that you can make that particle interact with the particle bacteria. So this is where I understand. So when I found that this can happen, then I started engineering my thoughts towards to the way we can lead us to some kind of desired value for what we are doing. So our first example was a long time back. We prepared some zinc oxide because we differentiate from environment. Now what is pH? pH is the concentration, the relative concentration of hydrogen ions, H plus. So what is hydrogen ions? It is nothing but a proton. It is lost in the electron. So only the proton is there. Now this proton is magnetic when it is approaching an electron cloud, it will modify electron. Right? So when it modifies the cloud, the bonding that was going to make with the cation or cation and the ion, that bonding is going to be affected. So you are modifying the bond strength or the bond length by changing the peak. So this was observed when we first made zinc oxide a few years back with different pH concentrations. And at a particular concentration, we found the zinc oxide exhibits a factor or phenomenon which is extraordinary in other things. Now, in this case, when the student came to me for a project, my daughter and her student and friends, I thought of giving them a problem on iron oxide. because iron oxide is the very least material in the discussion. And so that is the starting point of my involvement in this project. So we started with the intellectual properties of iron oxide, and that was cost innovation. Then, with days to come, we found out that they will change the pH and we will study the antibacterial properties. And ultimately, when these partners studied it down, we found that the pH not only affects the structure, it affects the surface charge, and that leads to the formation of the antibacterial properties. Now, hematite iron phase of iron oxide. This is the oxide. It is the negative monomer. It has a value of 0.1 kV. It is non-toxic. This is the level of fat. It is finding on the computer. Now, I am not going into those details. I am going into the methodology of this thing. Okay. So, where did we start? We started with a simple chemical hydrothermal synthesis. We took some chemical and then we precipitated the material and then treated it some high temperature security and we got the polite phase. Now, the thought of pH or pH or high pH is that. Okay. Now, from there, I will detail a little bit about how important these things are. Now, you see, in this picture, there are different types of hematite particles, nanoparticles. Okay? Some are round shaped, some are rod-like, some are clustered here, some are clustered aggregated here, some are very cubic. Okay? And all are hematite. This is a big chunk of hematite thing. And you can see there are several dimensions. Now, when this thing came to our mind, we found out that let's check what the different combinations of this structure can be. So this is the structure of the hematite surface of our material, and you can see the combinations. If you consider the planes can contain different combinations of the atoms and the atoms. One of them is containing only the iron. One of them is containing both, and someone can contain only the oxygen. Now, if you have terminations of these surfaces, then these will be accordingly carrying the charge of the cation or the anion or the neutral. So you can have positive surfaces, you can have negative surfaces, and you can have neutral surfaces. So, once like that, we have to examine what are the terminations of each and everything when we are changing our conditions. These are all efforts of different combinations of a synthesis process. So now it comes to our knowledge why different people have made different the same nanoparticles using a little bit of different process and then they are into different antibacterial properties or any other properties. So there is a direct correlation of how you are making and how you are telling nature to create the materials in a particular way. Now, so our hypothesis was we will change the parameter and see the structural deviation, and the structural deviation will give alterations in the biological properties. So this was our hypothesis. Okay. Now we prefer to make 3 different samples, one at pH 8 and the other one is 10, and then we targeted 10 12, but we could not achieve 12, so we constrained ourselves to 11.5. You can see from this image that the particle size has reduced gradually. Okay, so that is an indication that there is something going on in this material. Okay. Now, in the we first wanted to make sure that we are looking into the right material. So we did ETX. How many of you know what is the ETX measurement? Anyone? Okay. So ETX is a electron spectroscopy thing, where you use electrons to bombard on a material and throw out characteristic X-rays from the cations and anions that are present in the material. Okay? So those characteristic X-rays are specific to those elements which can help us detect those elements. So from this EGIC study, we could find that only iron and oxygen are present in this material. And the only other impurity is the adventitious carbon. Adventitious carbon is the carbon that we handle. Okay. So that is natural carbon that can exist in every sample. So our samples were extremely pure. That was the first test that we did to confirm that we are on the right path. Okay. Now, from here, we found that we did some DNS measurement. So this is a spectroscopic measurement where we can find the hydrodynamic size, the polydispersity index, and the zeta potential. How many of you know these parameters? Zeta potential, okay? Okay. Not many. So the zeta potential is a parameter which comes from the effective size of the material, of the particles. Okay. Suppose you have a small particle with a positive charge. It will attract the negative ions from the solution that it will get. Okay. So those ions will get fixed to the surface of the charge. But at some point, some of the ions will no longer be attached to that particle. So where the first particle starts slipping, that gives you the hydrodynamic size. Okay. And the potential barrier that is there between the two surfaces is called the zeta potential. Now, one of the most important thing is the polydispersive index. The polydispersive index, if it is lesser than 0.5, then it is called monodispersive. So the particle size, if it is small enough and the charge is also small enough, then it does not interact with the other particles. So that gives it the freedom of not interacting with other particles in terms of adhesion. Okay. So they are dispersed in the material. And these are very important parameters for all biological processes because that gives the freedom to the particle to interact with the bacteria or a cancer cell or anything else. So these are very important properties that we need to study. And we found that only the esteemed sample has a polydispersive index which is lesser than 0.5. That means this is the monodispersive one, whereas the other ones are a bit higher. One of the interesting points is the zeta potential, which is the potential of the particle itself, goes from negative to a little positive and it gets further positive. So it's a move towards a positive direction. Okay. So by changing the pH, we have achieved some unidirectional thing along this direction. Okay. Now this is very important. This is actually also controlling the hydrodynamic size because the charge is changing from the negative to the positive one. Okay. So you can see the hydrodynamic size is actually reached at this point. And that may be the reason why this is more dispersed. So there is some important thing which we can find in this study about this esteemed sample. So the pH has increased the positiveness of the charge surface. So what is exactly causing this? In search of this, what we did some X-ray diffraction studies. The X-ray diffraction studies, how many of you know what is the XRD? XRD? You know? Okay. So what do you find from the XRD? Huh? It's the structure of the material, okay? And each of these peaks contribute the information of a particular plane, okay, that are available for the atomic distribution in the molecule, in the atom thing. So the ratio of these particular plane depends on the scattering factor of each cation and anion that are present in the material. Okay. Now, what we found that we also calculated the UV spectroscopy, and we calculated the band gap. Some of your the seniors or batchmates are going to IIT Indore now to study these properties. Okay. Now the band gap also has a unilateral change as much as the surface gap. So, but interestingly, the RABVIT energy, I cannot take the class here, but it relates to the dislocations or the disorders in the material. Okay. So if you have a disordered system, in a crystal is a extremely ordered lattice. Okay. If you create a disorder in the lattice, it will obviously have changes in the electronic properties, and this is where it shows up. So you can calculate the RABVIT energy, and you can see that the RABVIT energy is the lowest at S10. So there is something in this S10 sample which is different than others. Now, so this is the exciting. Okay. So we started putting our mind into what exactly is different in S10. And what we found is that the different planes have different intensities. So what is the change between one sample to the other in terms of this intensity? We try to find out. And why do we need to find out? We know that it is from the scattering factor. So are more atoms with these elements are scattering more? That is what we are trying to find out. Okay. So we took the intensity ratios and normalized it with the 104, which is a neutral axis plane, and found that the only two changes that are happening very drastically consistently are these two, 21410 and the 10110 plane. This is a neutral plane, but this one is an oxygen termination plane, which is a negative termination. Okay, you can see this 214 is somewhere here. Yes. So this is the oxygen termination plane. So if this plane is on the termination side, then we'll have a negative surface. Now the intensity of this plane is going down gradually. Sorry. The intensity of this plane is going down gradually. Okay? So that means the contribution from the negative surface is going down. So this is one of the observations which made us rethink about how the structure is evolving with the change of the pH. This was mind-blowing, and then we also looked into the antibacterial studies at this point, and we found that the MIC, the minimum inhibited concentration, that is the minimum concentration needed to attain a 50% killing of the bacteria, is also minimum for this one. So we need the positive charge for this E. coli bacteria. So by reducing the charge of this thing and the zeta potential, we have achieved this point. So you see how directly it is correlated to the structure and how you make your sample. So whenever you make your sample, please keep this in mind, that just by making a sample, it does not mean anything until and unless you understand what is going on behind. Now, this is the correlation. We also studied the bond angle and bond length, and we found that one specific bond length, a bond angle, is very important, and it is matching with the MIC train and also the PTI train. So there is some correlation between these three parameters. This is somewhere we have got stuck right now, and we are investigating further. Now you can also look into the other correlations, which is also present in the hydrodynamic science and also the lattice parameters. Okay, so these are some sites which we are looking at right now. One of the other aspects that need our attention is apart from the pH, there can be other factors like what other ingredients you are putting into the solution, which can give you a new set of materials. Okay. So from 1990s, the green synthesis is one of the most important topics that has come up. And in biology, when you're going forward, you will come across this term, green synthesis, again and again. So green synthesis is a way to produce materials by eliminating toxic waste as much as possible, and it reduces energy consumption and is uses ecological solvents. Okay. So this is not that much needed. Okay. So green synthesis can be done using bacteria, fungi, yeast, and plant extracts. Okay. Now, out of this, I am a little bit inclined towards the plant extracts because it gives me freedom to make the samples in my lab. I don't have permission to deal with these three. So this is what we have studied so far. But for your information, bacteria and different strains of bacteria can be used to create metal nanoparticles. Okay. And these metal nanoparticles are generally not only the particles itself, but it is sometimes capped also by some organic components. Okay, and these are very useful actually for all our antibacterial or anti-cancer materials. Okay. Now, the fungi is an interesting thing, and this is of my interest because it can make metal oxide nanoparticles, and I am an oxide person. So I have some interest in fungi. So I am looking for a collaborator who can help me with the fungi part. Now, yeast is also here. But as I told, this is not much visible. Sorry for the mistakes. So there are plant extracts which are available all throughout literature. You can find out aloe vera, oat, alfalfa, tulsi, lemon, neem, coriander, mustard, lemongrass, etc. And these can be used for silver and gold nanoparticles, and then similar things can be used for oxide nanoparticles also. In fact, in our lab we have used turmeric, we have used curcumin, we have used ashwagandha and rose petals to create synthetic green synthesis. Okay. Now this I want to exemplify one of the greatest papers that I have come across so far. This is from chickpeas. The chickpeas can be used to make titanium oxide nanoparticles, which can be used as anode material in lithium-ion batteries. Who knew this could have been possible a few years before? This is possible, and we are now actually looking into these materials from the electronic perspective also. Okay. Now, the mechanism of this synthesis is actually divided into three different phases. The activation phase, where the reduction of the metal ions takes place. Now, this is definitely for a metal nanoparticle that is described here. But in the case of oxide nanoparticles, the activation phase is a little less, so that the oxygen can also react with the metal ions and form the oxide phase. But the other two phases are still the same. The growth phase, where spontaneous particles, they come and coalesce together and form bigger particles. And then the termination phase, as I said, the termination phase is the most important phase because that determines what the functionality of the material is. So you have to be careful about how you are designing your experiment towards the final product. Okay. So These two slides are key for. Now, parameters that can affect gene synthesis, as I told you, have to be careful. What are the things? Temperature is a very important thing. It affects the pH. While you are making the sample, it will affect your pH. So you have to be very careful about the temperature of the material when you are in the synthesis process. Because if the pH changes, everything will change. Okay. And then after the sample is extracted, you have to go for a sintering process or a high temperature. That is also very important. What temperature you are setting, because that is the termination platform. Okay. So you have to be very careful about these two processes. And then the concentration of the precursor, I detail it in the next few slides. The precursors that you are putting, how much you are putting, that will determine how much capping will happen, whether the size will go down due to the capping and other things, and a lot of other factors. And if the size goes down, then all the parameters will change. The physical parameters will change. Okay. Process kinetics, how fast or how slow you are doing this thing. So that will affect the entire thing. And then the absorption kinetics. How much the materials that you are making can absorb the materials that you are putting as a modifier. Okay. So that is very important. Now, this actually the grid synthesis gives us the freedom to modify the size and shape of the nanoparticles by tuning all these parameters. Okay, so by modifying the size and shape, what we get, we can change the functionality of the materials, leading to different devices, different biological applications, and different electronic components. Now, this is one example which we did here actually, your students did here, your seniors did. This is one zinc oxide which was functionalized with curcumin. So, zinc oxide is known to be anti-cancerous, drug delivery, antibacterial, and so is curcumin. So, we chose these two components. We found new materials, and what we found is we prepared the curcumin solution and the zinc acetic solution, mix them, added NOH. It seems very simple, but there are lots of steps in this process. And then we extracted the powder, washed it, and heated the powders and dried. Now, we found that we got very nice phase of this material, very phase pure. Although this is looking very simple, this took about 6 months to get to the bottom of that point. Okay? Now, here we found that structurally there is not much change, but the crystallite size has decreased. Now, when the crystallite size decreases, there must be something to do with the strain in the lattice. Okay? So that something has changed in the lattice. And we found that the strain has indeed been inconsistent. We are working on this. This two does not match here. There may be other factors which we are investigating at first. Now, the band gap, according to the crystallite size, increases gradually, and this is one factor that we are right now checking. The urban energy again is a little up and down. It does not follow a regular trend. These are things which are very new. We are still under the process of investigation. And you can see the crystallite size of these materials are changing. The formation is changing. Because the change is very much seen in these final concentrations. So this is just by changing the concentration of the curcumin solution. Now here you can see there is some change in the zeta potential, and there is some change in the polydispersive index. But most interestingly, all these materials are monodispersive. So this is one of the greatest achievements so far that we have been able to, with a very little amount of curcumin, we have been able to reduce the size of the materials to such an extent that we can have monodispersive materials. So the MIC studies were done, and we have seen that the MIC gradually decreases with the concentration. This is a very interesting observation, and it leads us to further investigation. And this is our final stage that we are looking at. So the newcomers, those who will come to the lab, will be doing this experiment from now on. I hope you have a nice time ahead. Okay, so these are some international collaborators that we have, and these are some alumni. We have quite a lot of papers coming out from our team, and in the last, since 2015, we have 101 papers. Now, why I am saying? Because these mostly interns contribute to this research, apart from the PhD scholars. So there is a huge possibility of interns to get into research and do something constructive. Okay, these are all placed abroad. Not a single person is inside now. Although you can see some of them are here, but inside. This girl here, Shikha, she got the best researcher award in Taiwan. Okay, she's in ACUT, Taiwan. And this guy is in Cambridge right now, Oxford right now, and she just got a job after graduating from and they are everywhere actually. So please pay your attention to research and get to a point where it's not just my lab, it's many labs are there where you can go and build your career and have a very nice future. Okay? Thank you. Questions?
You mentioned that in the appetite structures, you found correlations with. You mentioned that in the hepatite structures, you found some correlations with zeta potential, with the polydispersity index, with the hydrodynamic size, etc. In this specific case, how would you go about establishing the causal relationship between these factors and the particles properties?
Okay. So, to find out the science behind it is still a question mark. Okay? So we are trying different ways, but we have found out that by changing the pH, you are making changes in the bond length in such a way, at some point it is giving a minimum. Okay? And at that point, you may be generating some properties which are actually helpful to terminating some of the surfaces in a particular way. Terminating some of the surfaces. So suppose you have oxygen surfaces and iron surfaces, right? There is a ratio between the two. In a particle, suppose this is a iron oxide particle. This is the iron surface, this is the oxygen surface. Obviously, the oxygen surface is much smaller than the iron surface. So you have more positive charge than the negative charge, right? But now you think of reducing the structure in a flatter way, where the iron surface gets lesser and the oxygen surface gets more. At that point, you will have more negative charge than the positive charge, right? So as we see, the zeta potential has changed. So, and at the same time, the oxygen plane that was terminating has also reduced, right? So the negative charge is getting reduced towards the positive charge. You get the point? So the relative essence of the positive charge and negative charge is getting changed. Okay. So that leads to a point where you are getting the minimal energy for creating the smallest particle. Okay. That gives you the less PDI. And that helps you to get a better antibacterial product. Does it answer my question?
Sure, sir. Good morning, sir. Thank you for your talk. I'm Hemant, that my doubt is that you explained a specific set of criteria that affect the parameters, that affect the properties of the materials, such as the concentration and static properties. However, what if there are more general, wide encompassing properties, such as the area where the experiment is performed? If it is at a higher altitude, then there will probably be a change in pressure. Does it also affect the material properties?
Absolutely correct. It will. In fact, there are infinite number of things that you should be taking care of. See, in the last, I don't know anyone present from the last batch. Antik is there, but Antik did not take part in the thing. We had to choose a particular time frame of the day where the temperature, environmental temperature was fixed. Okay? So we have resorted to that level also. It's just not going to the lab and do something. Because if the environmental temperature changes, you are mixing the sample at that temperature. So you are basically changing the pH value of it. Okay. So it is very important to keep all the factors in mind. Why do we fail to reproduce the same thing? Because we are not keeping in mind that something, or by simple ignorance, we are not being able to understand what is going on. Okay. So the more you become observant in this type of research, the better results you will come.
And another doubt that I have is that when you spoke about termination surfaces, the plane, the plane is the one that the atoms at that plane are the ones to decide the surface charge of the sample. So when you are selecting a material, for example, when you selected hematite, you had an oxide mineral. But what if you had another mineral which has chlorine? Now both are negative charge. So which one do you decide to use as the nanomaterial?
No. Every material will have some atoms, will have some anions. Every material will have some planes which will be terminated either with the negative ions or with the positive ions. So when you have a crystal, as I say, it is just not a negative surface all throughout. Okay, it cannot be. It will have certain surfaces which can be negative, it has certain surfaces which can be positive. So it's a combination. How much of the surface of the positive type and how much of the negative are exposed? What is the ratio between them? What is the charge that is it charged neutral on the surface or is it having a charge? Even if the charge is positive at some point, what is the type of morphology that it is having? Okay, is it sharp paint? Then iron cannot come and attach to it, right? So there are several factors here. The morphology is a very big factor. Okay, you get the point?
Yeah, doctor. Thank you.
Yes.
Morning, sir. So, from your talk, I noticed a band gap and alpha energy was calculated using UV. Please give a light on us how to calculate alpha energy and as well as the band gap using the UV spectroscopy.
That's a class by itself. I can take a class if you give me the time.
Definitely, sir.
Sure, okay.
I will touch with you by email.
Sure.
And then second point. So I noticed that the zeta potential value for the ferrous oxide crystals, so pH 10 is approximately -4, 11 is around 17, and 11.5 is 22. And more viscosity index at 11 is 183, and 11.5 is 222. And when Yes, sir. S10 sample number S10 is 186 is HDS and the polydispersed is basically monodispersed and potentially around 11. The change of this pH and change of these parameters was said to be that plane termination, oxygen termination. And there is a huge difference in pH, but when it comes to the oxygen plane termination, the values turn out to be 2.7, 2.8, and 2.9. I have a slide at the bottom of that. The difference is only 0.1 in the case of termination of the plane. But whereas the change of the pH from 10 to 11 to 11.5 and 10 to 11, 11.5, the huge difference in monodispersity and polydispersity index and the HDS. Can you please elaborate on that?
Yeah, very good point. Okay. So the changes that you are seeing in the oxygen concentration of that thing is a fraction, right, of 1, right? So if you multiply in percentage, it will become something about 1% to 2%. Okay. Now that is not the only change. There are changes in the positive terminals which we are not observing in this one. Okay. So as the oxygen quantity is going, the negative plane contribution is going down, there may be other positive contributions which are going up. Okay. So the net change of the difference of the negative and the positive will be different. And that is what is reflected in the zeta potential. Okay. So if the negative charge is going down, then we will have a positive contribution to the zeta potential, which is being observed here. Now, when it comes to the hydrodynamic size is actually, we do not know where the hydrodynamic size will be minimum. Okay. But it is somewhere in between S and S8 and S10. So, to understand that, we should make more samples in between these things. Okay. So then we can directly correlate between the pH and the surface charge and this thing. Okay. But as of now, we have seen that there is a minima here. Means when we are going from the negative charge to the positive charge, there is some point where the accumulation of charges is becoming minimum. Okay. That gives rise to the hydrodynamic size becoming lower. And then as you go higher, it again accumulates charge.
What about oxygen termination? The value was like
The termination, yeah. Okay, so this is a very tricky thing that we did just to answer our quest.
really the only difference is the 0.1.
So you see, there are certain positive charge terminations. This is a 110 set. So these two did not change, but here there is a change. Okay. This is also reducing, but there was one, I forgot one which plane it was, I am not finding it here, where the ratio increased drastically. I am not finding this one, okay, in this one, okay, but that is one of the things, because you cannot specify how one plane has changed in a particular sample, okay, and what is leading to that? That is something which we have to compute and find out, okay. And why is it related? Any other questions? Yeah, please. Yeah.
Thanks for the wonderful talk. I just wanted to get another technical thing over here. So you calculated this. You calculated this stream. How did you do that? Utilizing XRD?
Yes. It was not XRD. We did Williamson Hall.
Yeah.
Yeah.
So the origin of that stream, is it? What is the origin of that stream?
Okay. This is a very good question actually. In this pure sample, you should not expect strain, right?
Yes. Exactly.
But yeah, theoretically yes. But practically, you never know where there is oxygen defect sitting, whether oxygen interstitial is sitting, where is the zinc vacancy sitting. So these will have immense effect on the lattice. So the strain is generated due to these things. And by changing the pH, you are actually inviting the trouble.
Yes, actually, I was coming to this point also because another thing that can happen over the like you are quite familiar with perovskite. A lot of work is on the perovskite. there what happens is this, not only the geometrical reasons, but it also occurs due to this spin frustration kind of thing.
Absolutely.
So do you think that will be occurring over here or not?
Obviously, if there's oxygen vacancy,
Yes.
right? There's an electron sitting there. You know how it can affect the entire system.
So that can also be.
That obviously that can also affect.
Thank you.
Any other questions? Students are silent. Okay, fine. So if you don't have any questions, then I'll shut down. Yeah, good. Yeah.
Sir, so I personally do not have any questions at the moment, but your talk was also on YouTube, it was being live streamed. So we do have a few questions from that live stream that the students are asking, if you don't mind answering.
Sure, go ahead.
Alright, sir. So we have a question from Arman. He says, making of silver oxide monodisperse can be done by two methods, chemical reduction and solvent. Do both of these methods give same results or different results?
So solvent, hydrocarbon and solvent.
He says chemical reduction and solvent.
Yeah. It can be done, obviously done, but the solvent process we are doing day and night in our lab. The problem with solvent is we get agglomeratic circles. Okay. What is the reason behind agglomeration? Because there are some positive charges and negative charges which are very strong in this type of materials. Because these are mostly rounded up in nature. Okay. So it has all surfaces exposed. So it has reasons for coagulation. Okay. So you do not get bone dispersed materials in solvent. The other technique, yes, it can be done. Hydrothermal is one of them. But the problem with hydrothermal is you cannot do doping and other things. Because then you do not know how much dopant has gone into the sample. Or how much melting itself is in the solution part and ultimately, and how much there is the yield. Okay. So how much proportion of each?
Thanks so much.
Any other questions? Yeah.
Hello, sir. My name is Divya, and thank you so much for the wonderful talk. I would be using a lot of complicated words and I might be a little off, but you had spoken about how in green synthesis you're also making nanoparticles with using plants and even fungus, right? So, yeah, come back. So my question is, even with those, are you trying to work with changing the planes so that you can find different properties, or is this something that you only focus on? Thank you so much.
So when we use this plant extracts or some other yeast or bacteria or whatever, so our main purpose is to use the reduction properties of these materials, okay? So that we can reduce the metal ions to either metal or metal oxides, okay? Now in the process, what happens when we are making these materials itself get functionalized on the surface of the material, and that adds up to a different level of complexity which can be utilized in our next utility. Okay, so it's both ways. It's not only just to make the materials, also to functionalize the materials. Any other question? Yeah.
Good morning, sir. As we are using metals as biomaterial, so as we are using metals as biomaterial, so if it is not perfectly compatible, so it can create various issues in body. So by solving one problem, aren't we inviting other health issues? Like we can take example of copper. So accumulation of copper can lead to the Wilson's disease. That's the one of the rarest disease in India. So how can we tackle?
How? That is entirely your choice, what materials you are choosing. Zinc oxide is good, titanium oxide is good, iron oxide is good, but copper oxide is not. So we do not choose copper oxide. But yes, copper oxide can also be used as antibacterial properties. Maybe for the skin purpose and other purpose it can be used, right? It depends on whether you are taking it inside or not. That totally is your choice. What materials you choose.
So can we say that zinc oxide is perfectly biocompatible material?
Zinc oxide has been used in many drug delivery things, including cancer and other things. Okay. So I think it's safe. I'm not sure. I have to check on that whether it is really safe or not. But yeah, people have reported these things. Okay.
To answer your question and a follow-up after neurotoxicity is another issue. If we are now working by concept of fundamental the level of how much is the threshold of size and whether it is toxic to the human body or in the water body is another question.
Okay, thank you.
Now I would like to call Subrina ma'am to appreciate our esteemed speaker, Dr. Samantha Singh.
The Bioengineering Club is a platform for life sciences and engineering enthusiasts to share their passion and skills to author projects, host events, and learn new facets about their course of study through a nuanced yet diverse community of seniors and freshers. Today, on the behalf of the Bioengineering Club of VIT, in association with the School of Biosciences, Engineering and Technology, I'd like to have the honor to invite Dr. Milind Ratnabharati, Senior Principal Scientist, Directorate of Soybean Research in Vellore. Dr. Milind Ratnabharati has been Senior Principal Scientist at the Directorate of Soybean Research in Vellore, India since 2012. He has received doctorate in biochemistry from National Chemical Laboratory, Pune, and conducted postdoctoral research in the field of plant genome mapping and comparative genomics at URGV Institute, Irvine, France, Virginia Tech, Plattsburgh, and University of Missouri, Columbia, USA. Dr. Ratnabharati has over 18 years of research experience in plant biotechnology and has made significant contributions to the genetics and genomics essential of legume crops, mainly soybean, groundnut, common bean, chickpea, and pigeon pea. As a research scientist at University of Georgia, he worked on comparative genomic studies of peanut allergens and disease-resistant genes. Mr. Ratnabharati is recipient of prestigious fellowships like INRA Postdoctoral Fellowship, France, McKnight Foundation Visiting Scientist Fellowship, USA, and many more. He has over 88 publications in this field. His current research involves the genetic involvement of soybean through molecular breeding, comparative functional genomic approaches, and genomic strategies for improving yield and seed composition traits under drought stress conditions. Today, Dr. Ratnabaki will be sharing his knowledge on biosensing applications in the food industry and plant biotechnology. Food producers in India are asking the increasingly efficient quality control methods to satisfy the consumer and regulatory requirements to steadily improve the vital industry. Biosensors can be used to overcome the disadvantages of the traditional methods of testing, which are expensive and destructive. Biosensors are affordable, rapid, and non-destructive. Today, we hope
We have seen that sometimes during rainfall season, there is a dry spell for 1 month or 15 days, there is no rain. So crops get affected, yield is low. On the other hand, sometimes there is extensive rainfall continuously. So that also affects the crops and the yield is reduced. So there are several challenges are there, and there was green revolution in the 70s, but now again revolution is needed to increase the production of agriculture. Next please. So on legumes, I will be talking about this soybean, groundnut, common bean, pigeon pea, and chickpea. So this topic, although I am given as the biosciences was given, but I will be discussing both shortly biosciences and also new advances in plant genomics. So in the biosciences are widely applied for food safety, and as we all know, some of the foods have allergens. When children they have allergy for certain foods, as adults also they have allergies, but we are not aware of things. In addition, we spend a lot of pesticides around the crops, fungicides, insecticides. So to prevent these pesticide, insecticide, biocides are needed. In addition, the pharmaceutical success are there. So for that also biocides are needed. So in this next slide. Most common allergens sometimes the meat are there, and nuts are there. So our working was on groundnut, peanut, and because the population is allergic to groundnut. But in radiation population there is a groundnut, and we don't have allergy for groundnut. But there is a huge allergy problem is there. And therefore, these biases are widely applied for identification of these allergens. Next one. Different type of devices are there. Based on enzyme-based biosensors, then cell-based biosensors, also molecular-based biosensors are there. So I'm not going to explain the whole details, but I work on how to identify the proteins in the plants which are causing these allergens. So I will discuss on identification of those protein encoding genes in the ground. Yeah. What we see is that it is not a single protein, but it is a large family of proteins. Large amount of proteins are there, which may cause allergies. 10 to 15 proteins are there. Now, how to identify where these proteins are located on which chromosomes? So that is very important. Second is that when the population, there are different proteins, family 1, 2, 3. Though 1 or 2 are more important, but other protein families are less important. So that we want to identify. Next. So 5 areas which I will discuss today is on diversity studies, then genetic mapping, gene tagging, and sequencing and functional genomics. So these approaches have changed the field of genomics, whether it's a human genome or microbial genome or plant genome. So all these technologies are very important for advancement for identification of genes. Next please. So first, most important is the germ plasm. We have hundreds of varieties of soybean, for rice, for wheat, or maize, and these are stored. The seeds are stored. For example, globally these these seeds are stored at -80 degrees, and there are cold storage. Even in Arctic, North Pole, these seeds are stored. So this germ plasm character is very important, and at our institute, huge germ plasm of soybean is available. and we do fingerprinting of those lines and then characterize this. Next, please. This I would like to share the paper which was published in 1995, so almost more than 25 years back. And this was on Visual P. Visual P involved is a tool car, tool car day. And in India that's the most prominent lighting. And this fingerprinting of Visual P was done in 1995. And the important point is that the same technology is applied recently. Technology is changing, lot of new advancement on fingerprinting, high throughput technology are there. But we want to identify differences between the lines, different varieties. So this technology is still rapidly changing. Next, please. This is a type of fingerprinting pattern where you can get by cutting the DNA or by DNA amplification. So we can see the differences in the different lanes, and these differences are able to identify one plant to is different from the other plant. So this technology is a key for all the genomics in either plants or human genomics. Next, please. Another is to identify the markers near to the gene. So in the center you can see it's a gene, and we want to identify the DNA markers which are present either on the left side or the other side. So this again, this technology to identify the DNA bands very close to the gene is very important for the improvement of soybean crop or any other crop. So this DNA marker technology is again changing, and a lot of high throughput approaches are there to apply this technology. Next, please. These are some of the examples you might have studied. These are from fingerprinting, and as I mentioned that now all these markers, the SNP markers are the most common. That is a single nucleotide polymorphisms, and high throughput sequencing approaches are used to identify the variations. Like as we have seen in the COVID, we want to identify how one strain is different from another strain. So these SNP single nucleotide polymorphisms are used for identification of variations. Similarly, in plants, we sequence all these lines, we identify the differences, and then pinpoint what is the difference and what is the change in the protein. Next, please. This is another important article I want to share. This one on chickpea. So I've been working on chickpea for a long time, and again, developing a linkage map is a very important. Whether it's a human genome, plant genome, or any other genome, we have to develop a linkage map. Like a city, it has a road map, all the locations are known. Similarly, in plants, we develop these maps, and the location of genes are confirmed. So this is again very important for all the organisms. Next. This is an example of the linkage map. So initially when 10 years back, 20 years back, these maps were not saturated. But now with the new technology, sequencing technology, marker technology, how throughput liquid handling, so these high density maps are created for all the crops. And even with this technology, very few crops have a high density linkage map. Hundreds and thousands of crops still don't have the linkage map, or we don't know much information at the molecular level. Next. Once this diversity is known and the map is created, then we move for the cloning and identification of the gene. That is map-based cloning, and this involves various steps, creating libraries like bacteria artificial chromosome libraries, and then pinpointing the gene, and then sequencing those artificial chromosomes. And finally, we get the information about the gene and the protein, either which one is causing the allergy. So once these proteins are identified, they are expressed in the bacterial cell. The purified protein is purified, and then we develop the senses based on those proteins. Next, please. This is the screening technique for bacterial artificial chromosomes, and here you can see the liquid handling machines, which automatically pick the bacterial chromosomes and then perform the sequencing PCR reactions. So these are very routinely used. And when I was working in France on genomics area, so these high throughput technologies are widely used in plant genome analysis, human genome analysis. Next, please. So groundnut I would like to do some in detail. Like this is a very big genome size. So all plants have different genome size. Some of the plant is small genome, some is a big genome, right? So the groundnut has a very complex genome and low diversity within the different lines, and it is very difficult to identify genes and markers. So we recently this whole genome of this groundnut was sequenced by the international group in the Hyderabad, research, and also some of the groups in Georgia. So whole genome sequences are being done for soybean, for groundnut, for pigeon to chickpea, and they are giving a lot of information about the genes, where these genes are located, and how we can improve these plants. Next. I would like all the students to focus on this figure. What happens in plants, a lot of duplication, chromosome duplication took place millions of years back. So if you can see on the top, there is a chromosome and the box indicates the genes. So this was there millions long back, and then there was a whole genome duplication. So whole chromosome duplicated. Suppose there were 100 genes, it duplicated to 200 genes. And after that, there is some changes, and again there is a duplication. So multiple round of duplications of chromosome has been occurring in the plants, whether it is a wheat crop or sugarcane crop or soybean, groundnut, and these we can pinpoint what time this duplication has occurred, and this duplication is helping us to understand how these genomes are changing, and then to pinpoint which are the genes where they are located and how many duplicate copies of the genes are there. So this is a very fundamental like part of nature, whole genome duplications. If you see in the sugarcane, lot of duplication occur and a huge number of chromosomes are there. In soybean, two whole genome duplication took place. One was around 50 million years ago, another was 10 million years ago. So that we have pinpointed, and then now we are able to identify important genes for soybean. Next. In groundnut, as I mentioned before, large number of allergens are there. So we identified 11 types of proteins are there. And out of 11 proteins, 3 of them are very important, which are called as AIH1, 2, 3. And these are very crucial if we can develop the groundnut variety which does not have these 3 proteins. So that will be very helpful for controlling the allergy for groundnut. And in US, if you see all the food containers, they have a warning sign that this food contains groundnut or peanut is there or not. So that is very essential. Next, please. This is just an indication of number of genes present for these 3 proteins, AIH1. And since large number of proteins are there, so even to make a groundnut free of allergy, we have to remove all these genes from the chromosomes, and that's a very difficult task. But first we want to identify how many genes are there, pinpoint their location, and then we go for removing these allergens. Next. This is a multiple sequence alignment which is necessary to identify the differences between the proteins, and this helps us to understand what is the diversity at the protein level for different seed storage proteins and different proteins in plants. Next. Another is the comparative genomics. We can compare different legumes or different plants. Like we can compare rice chromosome with the wheat chromosome, sugarcane chromosome, and this gives a lot of information about the century. And all surprisingly, the genes present in rice is also present in wheat and sugarcane, and same thing in legumes. Same genes present on different crops are conserved. Next, please. This is a figure showing the same genes which is present in first you can see it's this was a sequencing of all these allergy genes, and the red box indicates so many allergy genes are there in the groundnut, and so this was done by large scale sequencing of the bacterial artificial chromosomes. So all these genes have been identified. Next, please. Now this is a very interesting figure, and again I will say students to look at this one. On the top you can see is the peanut, groundnut, and the same gene which are present in the groundnut also present in the pigeon pea, then grape at the bottom, and the tomato. So these genes are conserved in all the plants, and that's a very important. Some locations are changing, but the distance between the 2 genes are changing, but they all are conserved. And if one gene is coding for one function, so in the other crops also it has the same function. So this information is very informative. If one gene is giving tolerance to drought, to a plant. So same gene in other crops may also give, or one gene is giving resistance to disease. So other genes are also conserved and have same functions. Next please. Now this is the latest technology of next generation sequencing, and previously when the human genome was sequenced, it took several years, 5 years, or the plant genome sequencing 10 years. But now with this technology, within a couple of days or within a week, you can sequence a genome, and huge data is coming out of this next generation sequencing. And this is the right time for all the students to learn how we can the data which is coming out from LGS machines is so huge that you need to develop those computational technologies you should know to handle this data and to analyze this data and to identify what is the meaning of these next generation sequencing. So a lot of development is there. Previously, these sequences were generating around 100 base pair sequences, then 36 base pair sequences are generated. But the data is coming in huge, large GB and terabyte data is there. So we are collaborating with several groups and with IIT Indore computation groups. So they are working on developing new algorithms to analyze this next generation sequencing. So they are using the soybean genome data. This soybean genome was sequenced in US in 2010, and right now more than 2,000 lines of soybean have been sequenced. So huge data is there, but how we can understand this data, that is very challenging. Next please. I was working on grapes, so I would like to share some information about this. In grape, we have to spray a lot of fungicide because there are diseases. There some powder is there, powder mildew disease, downy mildew, and the detection of this pesticide is very important. So in India, there is a grape research institute in Pune, and they are developing this biosensor technology to identify the pesticide residues. And if we want to export these grapes, so we want to confirm that the residue of pesticide is very low. So this is very important. And sometimes when I was working on this genome research, so our aim was to develop a variety which does not get this disease. So that was we were working on. Next please. Now this is the example of that powder which comes from the grape leaf, and so there is no like the natural control is not there. A lot of fungicide we have to spray, and that is in our vegetables and fruits. A lot of contamination is there. So what we were planning is there is a white species, and white species we wanted to identify which can do assistance for this powdery mildew. And if that gene is transferred to the cultivated type, then we can get the resistant grape variety. Next. So this was the white species named as Muscadania rotundifolia, and it has that gene. And if that gene we transfer to our grape varieties, it will not get the disease. So like this, from white species we can transfer these important genes and make our plants which can have more fruits or does not have disease or drought. Next. So last 10 years we have been working on soybean, and soybean like worldwide is very important crop. Most important is grown in Brazil, Argentina, US, China, and India is in the 5th position. And MP is the largest producing soybean state in the country. And after MP, it is grown in Maharashtra and a little bit in Rajasthan. But there is a huge scope that it can be grown in other states, in North East India or southern states. And what is the oil, food, edible oil of our country is increasing. And a huge amount of billions of dollars we are importing these edible oil because the production is very low. So there is a huge demand to improve the oil content, oil quality. If we can improve the oil quality, that is very important. And oil content, even 1 or 2% oil content, if we can increase in the soybean, that will make a huge difference for oil. Next. This is one example of screening the drought tolerance. So you can see there is one is control, where there is a continuous rainfall is given is on there. On the other side, these plants there is a shade, and then we will cover these plants for 10 to 15 days, and there is no water for 15 to 20 days. And then we observe lot of parameters using different biosensor technologies. What is the moisture content in the soil? What is the photosynthesis rate? So a lot of hundreds of parameters are measured, And using this parameter, then we analyze the sequence data and pinpoint the genes. So this is the way we screen the genotypes. Next, please. During summer also we grow them and again identify very important lines of the soybean which are drought tolerant, and then they use these lines to develop the new varieties. Next, please. So this is showing that we also do for different root trait also we analyze, and for waterlogging also we screen these plants, and for several years like 3 years, 5 years we continuously do screening, and after that screening this data is used to write the molecular level comparison to pinpoint the differences, polymorphisms and identification of the genes. Next. So these are some of the lines which after giving the stress also they are having good soybean pods and they are green, so these can be used for developing the new variety. Next. Another problem also we have seen the continuous rainfall is there, and this water stagnation also creates a problem. So we use stress for around 10 to 12 days, and this water is there all the time, and after the water is gone, then how much number of pots we are getting. So a lot of parameters we score. Next, please. So this is showing that there is some damage in the foliar damage of the plants after the water stress, and there are some new roots are also coming. So these physiological traits we score, and there is another area which is called as the phenomics. So phenomics also has a lot of automated platforms are there to record these traits. Next. Another, as I mentioned, the roots also we measure in the plants. So these are the big pipes, and after growing these plants, we got open the pipes and remove the roots, and after that we measure their length and what is the root diameters and all the other parameters of roots. Next slide. So these are some of the examples, and all the soybean germplasm is screened like this, and there is a scanner, and with the scanner we can scan these roots and identify the parameters, and then we use this for our analysis. Next, please. Now, as I mentioned, sequencing we are doing, so 300 lines we have sequenced of this soybean. So this tree shows the genetic relationship of these 300 lines, and it helps us to identify how these lines differ from each other. So this is very important data of sequence data of 300 soybean lines, and this will help us to pinpoint the genes from the important traits. Next, please. Now currently we are doing this genome-wide association studies. This is another technology where we can pinpoint a single nucleotide change which is associated for high yield or high oil content. So one SNP which can change the oil content or high oil or disease resistance or drought tolerance. So those identifying those SNP is very crucial, and we are doing a lot of studies to pinpoint those single SNP markers for this improvement. And this we are hopeful that these markers, the breeders who are actually doing the crossing and developing new varieties of soybean, they will be using these markers to develop soybean varieties which are tolerant for disease, drought, and oil content. In soybean, there is one important factor called trypsin. Trypsin inhibitor is there. So we cannot consume soybean directly. We have to boil this soybean always for 15 minutes. In India, very few people are consuming the soybean, but in US and other places, a lot of food consumption is there. But because of this trypsin inhibitor, we cannot directly use it, and we have to boil it for 15 minutes, and then only we can use soybean. So we are also developing technologies to remove those genes of trypsin inhibitor so that we can directly consume this soybean. Another is one gene, LOX gene is there, and due to that there is some off flavor, and people don't like the flavor of this soybean. So we can remove even those genes and make the soybean more like food use. We can more. So this is again the same SNP haplotype analysis is done, and again as I mentioned, new technologies are coming, and students can really learn all these technologies because this is an integrated field to do the sequencing, then do image analysis of all these crops, and then do computational analysis, and finally pinpoint the gene. So this is again genome-wide association studies. Next, please. Finally, we get large number of genes, and from that again we have to pinpoint which is the key gene. So all these technologies are integrated, and then we have to go for the functional studies. And functional studies involve pinpointing the stopping the expression of particular gene in the plant itself. So that we do using new approaches. Next slide. So this is the functional genomics where we stop the expression at the RNA level of the plant and then check whether one plant which is tolerant to drought becomes susceptible by stopping RNA level expression. So this technology is using the microarray where we do the expression studies. Then there is another technology called high resolution gene silencing, and also RNAi technology is there. So we can develop a transgenic soybean plant. So here I would like to mention that in the US, mostly the plants are transgenic. Like soybean transgenic plants are grown. In India, only transgenic cotton is there, VT cotton, and Bacillus thuringiensis gene was transferred to VT to protect from the insect. But soybean is not transgenic, and therefore there is some advantage because after extracting the oil, the meat is there, and this meat is exported to the European countries for animal food. So therefore, this non-transgenic, there is high demand of this non-transgenic soybean, and a lot of export to European countries, China and Japan is there. Because India does not have a transgenic soybean now. But now new approaches are coming, that is genome editing, and that is going to change the entire agriculture sector. We can pinpoint the SNP and change that, and make the plant very good for with a high yield, a good number of crops. So now our institute and all over India, they are focusing on this genome editing technology, and there is a huge scope to make changes in the plants and all other organisms through this technology, new revolution will be coming. Next, please. So this is a FLAG3 gene, which is involved in the oil quality. Oleic acid content is there, and if we can improve the oleic acid content, so that helps for our heart. So what we have found that if this FLAG3 gene overexpressed in the plant, that helps for drought tolerance. So this is one result from our experiments. So this was another gene which was silenced, and by silencing this gene, there is a drought tolerance is there, salinity tolerance is there. So all these technologies we are using to improve the soybean plants. Right? RNA technology, as I mentioned, that we can transfer a new gene to the soybean and develop it for drought tolerance and disease also. What we are observing is that new diseases are coming, and a lot of research is needed to control these diseases because due to climate change, new pathogens are emerging, and that is a very big challenge. Last 5 years have been very difficult in our country for soybean production. There is fluctuation, like reduced yields are there, farmers are facing challenges. But we are very hopeful with these new technologies, new varieties will be developed, and which will be helpful for the farmers. Next, please. So in summary, I would like to mention that genomics has a wide applications in plant industry, and as our much talk about biosciences, but for developing good food seeds, biosciences technology is also very important, and combined together, there is a lot of progress can be made in the field of agriculture. So with this and new approaches like big data analysis, as I mentioned, and precision agriculture, then IoT devices are also being developed for agriculture. So these technologies will make a big impact. So with this, thank you very much for your attention, and if there are any questions, I will like to answer.
I have two questions. One is, in one of the slides you mentioned that the genetic change was happening about few million years before, right? So how do you assess the time?
Yes, that's a very good question. So assessing the time. So these are all these plants like soybean, chickpea, which will be they originated from single plant. and sometimes log get diverged. So we know that the soybean and groundnut get diverged after log time. So when we compare the DNA sequence of soybean and groundnut, and there is a rate of evolution is there. So what time, how much region is changing. So there is a clock, we can estimate the exact time that how many years ago these changes have taken place. So based on those differences in the nucleotide sequence, the other part which is, and using the advocative in the transformation, we can again put that gene in the desired plant. So there is a routine technology there where a new gene in the plant can be introduced. And that is widely used, as I mentioned, in US, in other